So, what we left off talking about last time, which I know was quite a while ago at this point, right? That was a week and a half ago, almost 2 weeks ago was our last time we actually had lecture. We were talking about Huckel theory. And Huckel theory is actually a specialized kind of consideration for variation of parameters. So variation of parameters, if we've got a linear combination of functions, if our guess function is something like C1 psi1 plus C2 psi2, we're going to end up with this secular determinant. And this secular determinant we can solve if we know the Hamiltonian and we know the wave functions so that we can plug this all in and solve. And this is where Huckel theory actually does a couple nice things. And so there are some assumptions that are really important for this that I want to go over again. So, couple things. One, we have our sigma bonded network. Right, that sigma bonded network is going to be all of those hybrid orbitals that are taking care of the single bonds. They're going to have a bulk of the electrons, and it's going to be well defined by sp2 hybrids, which is kind of already wrong, right? The saying that it's well defined by sp2 hybrids is a good approximation, but it's not actually going to be completely true. Second assumption is the pi electrons are, let me get the wording of this right, are acted on. By an electrostatic force from the sigma electrons. So that single bonded network is going to create some electric field that the pi electrons are going to be influenced by. And so this is essentially going to say there's a potential field that's going to be interacting with our pi electrons. And then the third thing is pi electrons are delocalized. So this does a couple things that simplifies our lives. The first approximation tells us that all we really have to worry about for our wave functions is going to be, psi1 is going to be some 2p za. It's going to be some p orbital. It's going to be in the unhybridized. So we could actually pick any of our p's, right? We've got an sp2 hybrid. So we could pick px, py, pz, whichever one's not hybridized. I'm going to pick the z. I think last time I picked y, but we can pick any of them. I picked the z for a couple of reasons. One, the equation is easier. Two, that means that any conjugated system we're looking at is going to be, sigma network's going to be in the xy plane, hybrid orbitals are going to be in the z plane. But this is the first approximation, allows us to say the only thing I need to worry about is the p electrons. This is going to be two things. So this is my 2pz orbital on nucleus A, my 2pz orbital on nucleus B. So I can ignore all of the 1s sigma, 2s, 1s beta, 2s sigma, 2s beta, all of that, and just focus on the pz orbitals. And also when I go to count my electrons, I can just count those pi electrons, those p electrons. So that's thing number one. Thing number two, pi electrons are acted on by an electrostatic force. That helps us to find the Hamiltonian. This essentially allows us to define the Hamiltonian as a negative h bar squared over 2m del squared plus some potential v of the sigma network. And this motion is going to be particular to the pi electrons. So I'm going to put a little subscript pi. Again, approximation 1 says I get to focus on the pi electrons. Approximation 2 says I'm going to have some potential field that's going to be interacting. And then we're actually going to do things very similar to what we did with most of our cases, is we're going to define with these functions and with these wave functions in this Hamiltonian, we're going to define our different matrix elements and see how things simplify. And we're going to have a couple nice things about this. Again, there are always these benefits from picking different things. So 2pzb is normalized. Like both of those are normalized. They're not orthogonal because they're on different nuclei, but they are normalized. They're just, if you pull out your hydrogen-like wave functions equation sheet, the same thing that we've been looking at since week 5, you can look up what your n equals 2, L equals 1, m sub L equals 0 wave function is. It's going to be some normalized thing. So the nice thing about that is it's already giving us some information. Which pen do I have? So S11 is equal to 1, right? And if I defined that, that would be the integral of psi1 star psi1 d tau, where psi1 is just this 2pza. It's normalized. So I can simplify my secular determinant. The S1s are going to S11. Same thing's going to be true for the S2 too. There's a couple other things that we get. Let's see here. Other thing we get is we're going to define an integral. The integral of psi1 star Hamiltonian psi1 d tau. Now notice here, we don't really know what this is, right? We know that it's some potential field. We know that if we could define the hybrid orbitals, we could get this thing eventually. But we can just define this as an integral, the same thing we did with our Coulomb integral, our exchange integral, our overlap integral. We're going to call this integral alpha. Again, I picked alpha because I didn't pick it. Alpha is the typical thing we pick when we're doing Huckel theory. We're applying these approximations. We say this integral, this is going to be for H11. It's going to be an integral of alpha. You'll notice if we do H22, we're actually going to get the same thing in terms of value. Because all we've got is a positional translation, right? We're just moving our position. We're not actually changing any of the fields or anything. So that's also going to be some alpha value. This leaves us with two other parts we need to worry about. That is the H21. And we're going to do the same thing. We're going to have some integral. It's going to be psi2 star H psi1. And we can't actually simplify that much more than that, because if we don't know what that potential field due to the sigma electrons looks like, I can't say how this is going to operate on it. So again, I just define this as some beta. Now there's a catch that we're going to look at as we go to bigger systems. But in order for this to work out, we've got some approximations. Another thing that we have to do. So this H21 is only going to actually exist if the p orbitals are close to each other in space. We'll look at a couple examples of that and how we solve those. But as these orbitals get further and further away from each other, they're going to have less and less interaction with each other. In early Huckel theory, we would say even something like the S21 would have a 0, and anything that's even 2 steps away would be 0. So if I had a bigger, now I don't have anything more than 2 steps away because I'm dealing with a small matrix at this point. But if I wanted to do a bigger molecule, which we will, we would see how this thing comes into play very much so. This is also going to give us another approximation. I'm not a huge fan of this one. This is saying the PZA orbital This is a really common approximation, saying that these two PZ orbitals, if you imagine, I'll do a little sketch real quick. So again, Huckel theory is applied to a conjugated pi system, usually a network of carbons. This would be a situation where we have 2 carbons with a double bond. So I'm looking at ethylene, and now I have to challenge my artistic skills. So I'm going to have a carbon. That's the sigma network in black there. And that's going to be my p orbitals. And this idea that this is equal to 0 says that these two things don't overlap. This is kind of an old approximation we don't actually use anymore. It's convenient when we're first learning this because it lets us ignore some matrix elements. And it's also convenient when we're first learning this because in order to solve for this, it's very similar to some of our past integrals where you have to do a bunch of things. And again, one of the things that I really like about your textbook is if you go to, oh, now I have to remember which section it is. If you go in 11th ed, table 9C1 actually has what the 2p pi orbital overlap integral is. So it's solvable. It's not actually 0. It depends on this internuclear distance, and it turns out it's pretty small for carbons. It's not actually 0, but this makes our secular determinant actually pretty easy. So if I take my H11, my H22, my H21, and my S21, and my S11, all of those things, and I plug them into the secular determinant, I get something that's pretty simple. Are you ready for that? Okay, I'm going to plug things in. You should write a new matrix in your notes. But I'm just going to cheat and erase and put new things in. That goes to 1. That goes to 1. Those two things go to alpha. That goes to 0. That goes to 0. Those two things go to beta. So we get a relatively simple matrix. Again, one of the great things, probably the reason most people think quantum mechanics is actually very complicated, is because we so often hide things, right? This matrix looks really simple. You can solve for the determinant of this matrix pretty easily. However, those things are actually integrals that are relatively challenging to solve. And we've also made a whole host of approximations about which things we can and cannot ignore. And this idea of which things can we and can we not ignore is essentially everything that's happened in quantum mechanics for the last 30 years. Has been, what kind of guesses can I make? Which things can I ignore? How much accuracy do I want? Which things do I have to include to get the details I want? So I find the Huckel theory is a kind of a good introduction to what could we do with this. We define a system, we start looking for what can we ignore, what can't we ignore. And we start seeing what kind of results we get for that. So with the simplicity of this, is actually not that difficult to diagonalize. sorry, not to get the energy, I'm going to have alpha minus E squared minus beta squared equals 0. And then I'm going to solve for this E. I'm going to have like a plus minus beta. I'm going to end up with E equals alpha plus or minus beta. You can imagine adding the beta over, taking the square root of beta squared is plus or minus beta. And then I'm going to bring it back over, bring the E over. You end up with this. And essentially, this looks a lot like what we saw for the hydrogen atom. We've got some standard energy plus or minus some correction energy. We've got these two parts to it, the same thing we saw before. We can also talk about what these wave functions look like. And I'm actually, oh, shoot. Maybe I did this. Let's see if I did some. Well, I'm going to have to open up something. So I know that using the big screen doesn't work that well, but I think I downloaded the code I want to this main computer. So as soon as that warms up, I'll show you how we actually solve this. For a 2x2, there's a pretty simple process of taking these energies, plugging them back in, and solving for C1 and C2. And you end up with two answers because we've got two energies. We've got alpha plus beta as one answer, and we've got alpha minus beta as another answer. Still not knowing what alpha and beta are, we can go through a computational process. We can do a bunch of integrals, but often you'll just be told the experimental or the computational values for alpha and beta. Let's see here. Also, everything gets deleted off these computers, so I'll have to see. One answer is going to be phi plus, which is going to be psi 2pZa plus psi 2pZb. And then I'm also going to have phi minus, which is going to be psi 2pZa minus psi 2pZb. So I've got, again, the same thing we got for a hydrogen molecule. I've got a positive energy, well, I've got an increase in energy, a decrease in energy. I've got a constructive interference and a destructive interference. And most of this comes from this first approximation saying that we've got the bonded network. That really allows us to focus on to something that's like a one-electron system, and we end up with results that kind of look like that. If I wanted to represent that in these orbitals, in my plus case, I would have these things aligned so that my phases line up, and I'm going to have this positive type situation. Or I could have the opposite of that, where I'm going to have this flip in them from that negative side. I'm just going to flip it. One of these cases is going to be constructive interference. One of these cases is going to be destructive interference. One of these we would call a pi bonding orbital. One of these we'd call a pi anti-bonding orbital. Pretty simple. So in terms of how we solve this, let me share the screen. Sorry to the video watchers, you're not going to be able to see this. It's going to be some of you. So if you look on your screens in front of you, I wrote this simple little chunk of code. That's essentially, there's a couple different ways that we can simplify this. What I did was I said if I divide, let's do it this way. So in order to put this into code, I'm going to do a little bit of an extra simplification. I'm going to rewrite this instead of as one matrix. I'm going to write it as two matrices. I'm going to call it alpha 1 minus beta 0, 1, 1, 0. So this would be that one matrix would be alphas along the diagonals, minus betas on the off diagonals. Sorry, plus betas on the off diagonals. Where's my notebook? This is the way your book breaks it up in terms of diagonal elements versus off-diagonal elements. There's another way we can simplify it, but what I'm going to do is I'm going to do it the same way your textbook does it. And what I want to figure out is I want to figure out what does it take to solve that matrix. And if we plug this in, I'm just saying I want to diagonalize this. And it turns out that in MATLAB, diagonalizing a matrix, solving for a matrix is pretty simple. You define the matrix, and then you just call for the eigenvalues, which is the command I. They made it really short because it's so useful. So I go ahead and I run that, and what you get spit out, this is the diagonal matrix. So I'm going to have one where I have beta minus. So this matrix, the D matrix, is the diagonalized matrix. And it's going to be an alpha minus beta and an alpha plus beta. That's what the -1 and the +1 are. These diagonal elements right there. That -1 would be corresponding to this alpha minus beta case. And then this +1 would correspond to the alpha plus beta case. At the same time, I get these two vectors that correspond to those energies. And right now, looking at those two vectors is a little bit strange. And you're going to read them in columns. So we've got one vector where you've got 0.7071. Turns out it's 1/√2. And you've got another plus 0.707. That's going to be this plus case. What I have here is the unnormalized version. When you do eigen, it actually also gives you the normalization. And I just happen to know in this case it's 1/√2. And then you've got your second vector, which is this one, that has a positive and a negative version. That's going to be this guy. Again, with a 1/√2 there for the normalization. Why is it nice that we do all of this? Well, if this only worked on a 2-carbon system, it'd be a little bit boring. So let's expand this and look at what happens if we go to a... I'm just going to skip 3 carbons. I'm going to go straight to 4 carbons. Are you ready for it? Questions yet? Okay. Try to beat me to this. I've got to erase the board so you get a little bit of a head start. 4x4 secular determinant. Go. Write it as generic as possible, and then we'll apply the Huckel approximations to see how that gets easier. Okay. Here we go. Okay. Hopefully, We wrote something like that. Take your time. Keep going. Right, we're just counting through everything. And then, well, sorry, I'll wait a moment. Wait a moment. It's okay. Right here. I'm going to do it down here, so I have a little bit more space. So this would be like looking at a 4-carbon system. We're going to label them carbon A, B, C, D. You could also label them 1, 2, 3, 4, but you know that would be the A, B, C, D would be for how we define the size. Psi 1 would be a 2PZA, Psi 2 would be 2PZB, Psi 3 would be 2PZC, so on and so forth. When we apply the Huckel approximation, a lot of this stuff simplifies. First off, applying the Huckel approximation is going to give us the same thing along the diagonal, because it's always going to be, essentially, if I just looked at this one carbon, carbon D, that's going to look like just like looking at carbon C, which is just like looking at just carbon B, which would tell us all the diagonal elements are actually going to be the same. They're all going to be alpha minus E. Those are my diagonal elements. Because they're all going to be the same integrals. They're all going to have that minus E term. All of the S31, S21, S41, all of those are going to be zeros in our first beginning approximation of Huckel theory. And the H21, this is, oh, I erased it. Why did I erase that? If the carbons are next to each other, H21 has a value of beta. If the carbons are split from each other, our first approximation is those carbons don't have an interaction. So I'm going to end up with a matrix like this, where along the diagonal, I've got my alpha minus E, because all those integrals are all the same. And then anything that's 1 away from the diagonal is going to have the value of beta. Anything that's 2 away from the diagonal is going to have a value of 0. With the approximation we're doing, we can split this the way your textbook does into 2 different matrices. A diagonal matrix in terms of alpha and a non-diagonal matrix in terms of beta. So this is going to be alpha. We often will represent this in a simple way as alpha 1 with, I don't know what that, tilde under it, or however you represent matrices. So that's our identity matrix, our 1s along the diagonal matrix, plus beta 0. Oh, 1, 2, 3, 4, 1, 2, 3, 4. I gotta make sure I don't mess up. This is on camera. There we go. And I can look at this as this is my psi 2PZA. Or let me give myself a little bit more space. I'm going to write the same thing, so don't worry if you wrote that down. You're writing the right thing. So this is going to be psi 2pza. This is going to be psi 2pzb, psi 2pzc, psi 2pzd. And what I want to find is I want to find what combinations, how do I add these rows together, subtract them, multiply them by some value to get that to be diagonal. Questions?
So alpha 1, that's the identity matrix for 4x4?
Yeah.
Okay.
Yeah. That you don't know offhand that it's for a 4x4 unless you also look at the beta matrix next to it.
For that one.
Yeah. It's the identity matrix for any n by n matrix.
Okay.
Was that your same question? So all we have to do now is figure out how we add these different columns and rows together to get something that makes it diagonal. I'm not very good at that, so again, to your screens, to computer. The computer, I've already, hopefully I've done this correctly. Whew, yeah. I did it in a little bit of a different way. Let me change this just a bit. I left the alphas in there. I'm going to go ahead and turn those into zeros. So I'm going to diagonalize this matrix associated with beta. By just changing my code, all I have to do is change it to do the eigenvalue of my matrix B that I have defined. How many energy values should you get for this 4x4 matrix when you get the answers for energy? Show me with your fingers. How many answers do you expect to get for a 4x4? 4. How many wave functions do you expect to get? Also 4. There's going to be some combination of these things for each one. So when I run this, I should get 4 vectors that will, the matrix that diagonalizes this that has the right combinations of each of these. And I should get 4 energy values. And wow, that ran really fast. So here is this D matrix. That's the diagonalization matrix. Those are going to be our 4 energy values. And what we get, if you look at it, where did I put my green pen? Ah, there we go. I'm essentially going to get 4 different energy values. I'm going to get alpha minus 1.6. Someone read that number. I can get it. 618 beta. I'm going to get alpha minus 0.618 beta. I'm going to get alpha plus 0.618 beta. And I'm going to get alpha plus 1.618 beta. Those are my 4 energies. For each of those energies, I also have a function associated with it. I'm just going to write one of them. So I'm looking at that 4th column. And you notice it's the one that has all positive values. And I can't remember what those correspond to. They correspond to like a 1 over root 4 or something, or a 1 over root 3 or 1 over root 6 or something like that. But I can't remember, so I'm just going to write it down as a 0.3717. Psi 1 plus 0.6015. Oh, that's double, isn't it? 6015 psi 2 plus 0.6015 psi 3 plus 0.3717 psi 4. Where I put it as psi 1, psi 2, psi 3, psi 4 because I got tired of writing 2pza, 2pzb, 2pzc. But those are what the psis are. So it's just the linear combination, which I'm going to represent here. If I take those factors into account, which again is easier to see on your screen, but essentially what we've solved for, that vector is one of the solutions, is one of our C1, C2, C3, C4 combinations that solves this. Yeah?
Are you not worried about the negative?
Is there a negative? Oh, no, I'm looking at the 4th column because I wanted the one that was all positives.
Okay.
So I'm looking right here. I'm looking at that one. The negatives definitely matter. I'm looking at that fourth column because I knew it was going to be the lowest energy. So if I wanted to represent this on a picture that has my different carbons, I would essentially say, look, all of these are going to be pointing in the same direction. The first and the last one are a little bit smaller, and the middle ones are a little bit larger. But they're all pointing in the same direction. That's my highest energy. That's my most stable state. This gives me one of my possible conjugations of the electrons just moving all across the top and the bottom across this molecule. I could also, and I can now do this for all four of these. Right? So I've got this one, then I've got the next one where it's the first two are inverse, the next two aren't. I've got the next one where the middle two are the same and the edges are inverse. And the last one where it flips back and forth, back and forth. Yeah?
How do I know that this is the lowest energy?
So, a couple things. The main reason that I know this is because this situation where everything is symmetric is going to be the lowest energy case. The other information that becomes handy to know is the way that alpha and betas are defined. You're essentially going to have both of those be negative. And since this is an energy well, when alpha and beta add together, that's going to give you the lowest energy. So the largest alpha and beta addition, which is why I also wrote it in this particular order, was I wrote it from the one that's going to have the subtraction that's going to be a higher energy because you're subtracting a negative. So you're going to be moving out of the well, to the adding a negative, which is going to push you deeper into the well. Questions? Yeah.
For the 5-4, is that the bottom row on this?
No, it's the one that's in the green box.
Oh, so they go vertically.
Yeah, they go vertically for when we're looking at our new 5s. Right, so essentially what you do when you diagonalize this is you change that psi 2 PZD into 5-4.
Oh.
And then those are the coefficients of the old functions to get this new function.
So the V matrix, those are all the parameters?
Yeah, so that V matrix is 4 sets of 4 coefficients. Right, so when we look at this, we're actually going to have plus C3 psi 3 plus C4 psi 4. I forgot to change that part of it. So what that V matrix is your 4 sets, because we've got 4 different energies, of your 4 parameters, C1, C2, C3, C4. Yeah?
Is there a way, wouldn't you could just set like the diagonal row all to x and then solve for x and then you'll get like also your 4?
Yes, that also works. So there's depending on which textbook you're looking in, there's a couple different ways that you can set this up. Another textbook I like divides this matrix by beta, and then you get all of your betas become 1s, and your alpha minus e divided by beta you call x, and that also works.
Right, because you're saying x is equal to alpha minus e over beta.
Yeah, yeah. Yeah, so there's several different ways that you can set this up and it works. The main thing to look for is you've got diagonal elements where you're solving for your energy, and you've got off-diagonal elements. And you can imagine, maybe, if your off-diagonal elements were zeros, if you had a matrix that was already diagonal, you've already got answers. You don't have to do anything at that point, but you're ignoring all of your cross terms, which actually matter. Your H11, your H13, your H11, your H23, all of those shouldn't be 0. And that's where this beta matrix comes in. So I want to show you one more, and then I'm going to let you do a MATLAB thing together. And the last one I want to do is, instead of doing a line, I want to do a ring. So I'm going to do my best to draw this. That's not going to work. Let's try that again. So I'm doing a 4x4 ring. So I'm doing another 4x4 ring. In this case, this would be cyclobutadiene if I wanted to have a conjugated pi system. And I'm going to have something that looks like that. If you can imagine three-dimensional, it's laying flat into the plane. We've got our p orbitals. And we're essentially going to have the same Huckel matrix with a slight tweak. Tell your neighbor what you think the slight tweak is. So, which things should I change in my matrix? Corner B's. Why do I have the corner B's? So notice in this case, if I label these 1, 2, 3, 4, 1 and 4 are now next to each other. So this 0 is my 1 and 4 being next to each other. And this 0 would be my 1 and 4 being next to each other. So I end up with corner B's. Corner betas. So that's actually pretty easy to change in this code that I've got set up. So all I'm going to do is I'm going to modify my code here. So, maybe it's not that easy. Okay, so that one needs to be a not 0. That needs to be a 1. Right, okay. And then this last one, we need a 1 there. So it goes 1, 0, 1, 0. Good, okay. So I've modified my B matrix. And going through the process of diagonalizing this would be a little bit of a headache by hand. All I'm going to do is hit this run button. Here's my new matrix. I end up with, oh, that's funny. I don't know why it made those all negatives. There's probably something wrong in the way that it finds signs. But the point is, they're all pointing in the same direction, right? So I end up with 1, 2, 3, 4 energies. I've got -2, 0, 0, and +2. And then I've got my 1, 2, 3, 4 sets of answers. And what I'm going to do real quick is I'm going to try and draw these 4 answers. So we can look at one more thing. And then I'll let you do some stuff. So I've got to draw 4 of these to represent my 4 answers. 1, 2, actually, let's do it this way. This will be fun. Fun is relative, but 1, 2, 3, 4. Not quite symmetric. Pretend I can draw. Can you tell the reason I did it this way? Look at the energies. All of them pointing in the same direction. Let's see. That next one is going to be 0, down, down. I've got another one where I actually have 2 of my vectors end up being 0. And I've got the other 2 pointing in the same direction. Then I've got another one that's kind of a shift from that. Right. Oh, wait. So this would be, yeah, let me go ahead and label these on the screen. That green one is this one. That red one is this. The black one, oh, that's not black. The black one is this other one. And then I've got to draw the last one still. Question.
Is the red one supposed to be opposite spins on the sides?
Oh, they are. Yes, they are. They are. Thank you. I was a little worried about that because I thought these two should have nice symmetry. They should look the same, just rotated, since they have the same energy. So thank you for catching that. And then this last one, let's see here, is going to be flipping back and forth, back and forth. So it's going to go like plus, minus, plus, minus. So I've got this case that's really symmetric. It has all the positive phases on one side, all the negative phases on another. I've got this one where it's constantly flipping back and forth. That ends up being higher energy. Question here, then that.
So what's exactly happening at the dots?
The dots, there's essentially, there's no orbitals there. So there's the solution to that, the solutions to these have no electron density, no wave functions represented on those two carbons. So essentially, those are saying there's no electron density on those two carbons for that solution. Question?
What do the phases like basically correspond to?
Oh. So the phases correspond to the e to the I phi term. Right, so it's kind of like a cosine phi, sine phi term that can either be in phase with each other if it's e to the plus phi, e to the plus phi, or out of phase with each other if it's e to the plus phi, e to the minus phi. So looking at those kind of that phase term, which we usually neglected in general chemistry, we're just like, oh, don't worry about it, they're plus and minus, but it's actually the I phi term, e to the I phi terms. Question here and then there.
Okay, I'm looking at like the top one, the bottom one. Like if you like just change this, if you put positives where the negatives aren't on the top one, when you do the same as the bottom one, can you do that?
Oh, you know what? I totally screwed these up. These are supposed to be positives. That's why. Yeah, I messed that up. Yeah, it's supposed to be alternating. Yeah. Those are supposed to be pluses. Yes, absolutely. They're supposed to be alternating. Right, and you can see that in the function on the screen where it goes plus 0.5, minus 0.5, plus 0.5, minus 0.5. Right, so it's alternating, it's flipping back and forth. Same question. Okay, yeah, I was supposed to put pluses there. So what this has done, and then I can translate this picture into an energy level diagram for this cyclobutadiene, where I'm going to have 4 energy levels. I'm going to end up with 4 electrons in it, 1 pi electron from each carbon. And then I can calculate how much energy is in those by saying this is going to be 2 times that energy plus 1, 2, 1 of that energy plus 1 of that energy. So we can start thinking about this in terms of the energy of the molecule. Homo-lumo gap, 1 through 5. Homo-lumo gap. So when we talk about this, when we look at optical properties associated with this, I'm going to give myself a little bit more space. When we look at optical properties, we're looking for the highest occupied molecular orbital to the lowest unoccupied molecular orbital. So I'll say that again. Highest occupied molecular orbital to the lowest unoccupied molecular orbital. It's called the Homo-lumo gap. So when I look at this, I say, okay, where's my highest occupied molecular orbital? That's my highest occupied. That's my lowest unoccupied. And my highest occupied can be either of these because they have the same energy. This tells me that most of the optical properties I'm going to see associated with this compound are going to be associated with that change in energy. That's where I'm going to see some optical properties associated with this electronic structure. That's the transition from the highest occupied to the lowest unoccupied is where you're going to see your optical properties, your first optical properties. Yeah?
That's not the band gap, is
Not quite. It's getting towards band gap. So in order to get to band gap, you have to look at not just an individual molecule, but you have to look at a network of molecules.
Okay.
And then you start getting these averaged to, you start getting, instead of just having 4 lines, you get 4 lines for 1 atom, 8 lines for 2, 400 for 100. And when you start to do that, you start to notice that you get, like, they all kind of are close to each other and you get bands. So we could move towards that with these calculations. We could get to bands. That would be for a large number of molecules, not just an individual molecule.
So it's the macro physics instead of the.
Micro, yeah, exactly.
Oh.
Yeah, but it's very closely related to each other. Other questions? Okay, so what I want you to do with the next 20 minutes or so is I want you to pull up the PolyLearn page. There's a MATLAB assignment that I'd like you to try and get through right now. The code that you need to write is relatively simple. If you look back at my screen, you'll notice my code is 4 lines, and I don't need 3 of those lines. Or I guess I don't need 2 of those. I don't need 2 of those lines. So the code is relatively simple. What I really want you to focus on is creating different systems and trying to figure out how you can translate that to these types of ideas that we've talked about today in class. I'm going to go ahead and stop the video.